Reinforcement learning is a huge topic, and there are many ideas in reinforcement learning, and I've done it for financial markets. Algorithmic trading using reinforcement learning. But before we start, it is good to know some great researchers in this area. Chaba Zebzewari, who has a very great book about reinforcement learning. Also, please watch the lectures of Peter Abil and also Sergey Levin. Please watch them in YouTube. It's available. And everybody knows Richard Sutton for reinforcement learning. And there are lots of paradigms. As I said, reinforcement learning is neither supervised learning nor unsupervised learning. It's a new paradigm. And nowadays, because of the advances in deep learning, or let's say not control theory, advances in optimization and let's say deep learning, it has now become attractive again. And so you know the basic stuff. You have reward, as we have in our brain, and we have environment. Our environment could be like Atari game, chess, self-driving cars, or even some abstract things. And it has been used for games as well. For example, here we have jump right or jump left. These are actions. For example, if you're in this state, if we do an action equal to jump left, then we reach to this state. And reinforcement learning, so we have a set of states and then set of actions and transition probabilities. Transition probability like Markov chain, transition probability of Markov chain. But here we have an action as well. You only need to know the state and action in order to go to the other state. So if you are in this state, if you know this action, then with some probability you go to another action. And this is the goal. So you sum all of the discounted, we discounted by gamma. Gamma could be 0.9, and then the rewards, given some policy. And a horizon, in control theory, it depends, for example, finite horizon predictive control, because my background is electrical engineering and nonlinear control. So in there, we were controlling nonlinear systems, for example, a nonlinear robot or any nonlinear control system. You could have infinite horizon, see what happens at infinity. For example, at infinity, it approximately reaches some level. In deep QNet, because of advances in deep learning, we can now approximate anything, but it's a little bit different because when you are in this state, the way that this neural net is learning affects the next state that you put in. So it's not IID data that you're giving to this network. So it is a little bit more difficult, and that's why it's not straightforward to just pick some architecture and then put it in PyTorch and that's it. No, it's more complicated than that. So we have a state transition probability, as I said, but we have immediate reward function. This is immediate reward function. And return is discounted by this gamma. And just like financial theory that we have, and money is, the value of money changes because it is you should add the discounted values. So it's almost the same thing. And in gambling is a good example. In reinforcement learning, you can have these dynamics. So S is just 1 or -1. and you have a reward system, and we want to reach this level. And the policy could be either deterministic, but it is not interesting. So another way is stochastic policy, which is more interesting, especially in control theory, stochastic control, stochastic, even in reinforcement learning nowadays has become very popular. Many of the algorithms are just based on stochastic policies. And the value function is one of the first things that came to mind. I mean, the works of Richard Bellman and those things. And so given some state, when x0 is selected at random, you have a value. And this is the expected discounted sum of discounted rewards. And of course, this one is more general than this one. And then when you subtract them, we will talk about advantage and those things that we need for trust region policy optimization in the third lecture. I will talk about it in the third lecture. So ordering matters just like you do in Banach spaces, Hilbert spaces, but more generally Banach spaces. Now here we can define such an order. And there are many ways to define this order, and it is very important from theoretical perspective. And the optimal policy and optimal state value function are just the maximum over all policies that you have tried. You enumerate, for example, you have infinite memory, you can enumerate all of the policies and you can select which one is the best. So this is the naive approach to maximization. And the optimal value function and action value function. So if the supremum of all these Qs is V star. And it's easy to verify that this relation holds. And we want this to converge iteratively, because the analytical is just restricted to some trivial and easy examples. But the Bellman equation for deterministic policies, let's say, we can define a Bellman operator such that the fixed point of that, so people are familiar with Banach spaces and fixed point theory in dynamical systems understand what I say much better. And the Bellman optimality condition, so here it's different because you have supremum and this makes it nonlinear, and that's why this nonlinear operator is really hard. For example, finding such a weird fixed point in that space, that complicated function space. So after a while, you want to converge to this fixed point. But because it is nonlinear, so it is not straightforward. So it's a little bit difficult. And you see, T pi is linear. Of course, affine linear. But T star, because of this supremum, is nonlinear. But both of them are, we call them Bellman operators for historical purposes. And dynamical programming for solving Markov decision processes is a classic thing that, for example, we iterate over the values, also for the Qs, and this relation holds. If you want to do some theoretical work, you need these equations. And the value iteration, so we start from some, so all of them is iterative. I mean, when you're just one step till the final target, till the final step, or two step or k step, iteratively you can solve this optimization very easily. I mean, this iteration, but there are two fours, because one of them is for the horizon. For example, if you're if you are in the second step, two-step till stopping, or three-step or H-step till stopping, you have just started, you go reach several places, and so you have lots of trajectories. But we are not talking about policy optimization yet. So the first algorithm that came to mind was these value iteration methods, because we know that it converges. Value iteration converges, and it's a theorem. So don't worry about the infinite horizon as well, because as this term, this term is less than this term, but because each of these terms are less than R of max, so it becomes R of max gamma H plus 1 plus, and this is a geometric sequence. In high school, this is just this one. And that's why this converges to this, and that's why we don't need to worry. And that's a peculiar motivation for using gamma. It's just for theoretical purposes, to make this convergent and to make our theoretical things more valid. And we could have three actions. For example, we only pick one, this one action. For example, when we are in C, if we pick action 1, we reach state A. But if we pick action 2, we could go to state D. So there are 4 states, A, B, C, and D, 2 possible actions, 1 and 2. And the probability of going, if you have some state and given an action, the probability of going to the next state is like this. But just 10% to go to a wrong direction. And if you calculate this Bellman equation, you will notice that it's just an iterative thing, because it appears, for example, this one appears here. So after some calculations, we can understand the value function. You can do the same thing for the second action, which is only pick 2. Also, the third one, which is a mixture of 1 and 2, the first and second action. But we'll notice that the third action, which is the mixed one, has better value functions. So this is higher than 75 and 75. This is higher than 68 and 87. This is higher than 87 and 8 and 68. And so mathematics compares the most diverse phenomena and discovers the secret analogies that unite them. And so let's start by the second lecture, which is value prediction algorithm. The second lecture is value prediction problem. And so we have lots of reinforcement algorithm. It is model free, it could be model based. But in the third lecture, I will talk about policy optimization methods. In this lecture, I will talk about temporal difference here. I will talk about a little about Monte Carlo. We have talked about Q-learning and deep Q-learning already. So, of course, model-based approach is more useful in robotics, because you need to know if you want to design a nonlinear controller for a nonlinear robot or nonlinear control system, then model-based is more used in the control literature. But in model-free approach, sometimes we don't know even the model, and we want if we know the model, we want to escape it, because most of the time we don't even need it. And also actor critic method is very important. Maybe I will talk about it in lecture 4. And so there are lots of paradigms, but dynamic programming is the most historical one. But nowadays policy optimization has become very important, especially actor-critic methods, which is the gap between dynamic programming and a policy optimization. So it's a hybrid. And as you see in dynamic programming, you should try everything. So it takes time, but in temporal difference, you come here. In Monte Carlo, you get the actual return. This is the full return. But here you try to approximate it, at least, for example, TD0, this is the zero, the least approximation. That's why only RT plus 1 plus gamma VST1 is enough for you to approximate it. In order to know the difference, I mean, you should go along to reduce the error. Just like you do in control theory, you want to minimize the error. And that's why using this iteration, after a while, you understand your actions and your value function converges. And the temporal difference learning in finite state spaces is very easy, especially if your states are finite. And temporal difference learning learns from episodes of the experience. So it is model-free because it requires no knowledge of Markov decision process transitions and rewards. So you don't even need to know those transition probabilities. And learns from incomplete episodes by bootstrapping and updates and estimates towards another estimate. And depending on off policy, temporal difference learning, or on policy, we have Q learning and SARSA. And in temporal difference learning, as you will see, it's just this update. And for the Monte Carlo one, we just the reward is just driven from, for example, S minus gamma to the S minus 1 minus T, or when T is equal to 1, when S is equal to 1, it becomes 2. And then, so it's a little bit different from the TD, but this is also a kind of TD. And I mean, it's a kind of value iteration method. Still, we are not talking about policy optimization. And as I said, depending on that alpha that I said, for example, 0 is the simplest one. The simplest approximation is TD0. It's like a Taylor approximation of a function. You see, you have a complicated function. You approximate the first order maybe locally, and then you capture the second dynamics, and then you capture the third and lots of other, because you are increasing your neighborhoods. So you are adding more complicated things. So it's like Taylor approximation, Taylor series. And so we can also unify these Monte Carlo and TD. And what I want to say is that for large state spaces, we have too many states. So we cannot handle it because we don't have infinite memory unless we have some quantum computers that deals with memory in another way. But we cannot handle it. So in just like uncountable or uncountable Markov chains, which is still a problem. Because finite Markov chains is easy. It's just linear algebra. It's nothing. It's already solved. You cannot write a paper anymore. I mean, people still write a paper, but for uncountable Markov chains, there is nothing. There is nothing in the literature, almost nothing. Of course, there are some great computer scientists in Israel or USA that are working on that, but still we have a limited knowledge about uncountable Markov chain, which is really interesting, and it's related to the work of 3D.